So pretty clear picture is, we got the two masses and pulley and strings and stuff. Got some force being exerted by gravity. Okay, now gravity just means that the Earth and this thing attract each other so that this thing is attracted toward pretty much the center of the Earth, okay? And this one is attracted toward the center of the Earth. Now, if there's more mass on one side than the other, it's going to get the greater force, okay? Because everything has the same acceleration. As a result, everything, if left to fall freely, will accelerate toward the center of the Earth at the same rate, which is around 1,000 centimeters per second squared, closer to 980, and then variations due to altitude and composition of the Earth's mass in the vicinity. Okay, well, so you got some force of gravity in this, some force of gravity in this, right? Those forces are vectors, but I'm not going to indicate them as vectors. I'm going to say, here's the magnitude of the force, here's the magnitude of the force. The arrow indicates the direction, right? So this force tends to accelerate the system in what we're going to call the negative direction. Now, why do I call this the negative direction? Because it's clockwise. Counterclockwise is a positive direction. Okay? There's the positive direction of rotation. If you have an X and a Y axis, and you have something at this position, the position that's indicated by this vector, and a force that's indicated by this vector, that position is positive and that force is positive according to the directions of the X and Y axes, right? Well, if you multiply a positive force by a positive position, you get a positive tendency to rotate, okay? And that's not a totally specific statement, but that's one way you can remember that positive is counterclockwise, because in this situation, rotation tendency would be counterclockwise, right? Okay, so this force then tends to accelerate the system clockwise. This force tends to accelerate in the positive direction, right? Well, the net force is the sum of all the forces. Okay? Net force is the sum of all forces acting on the system consisting of the two masses. Now they're connected by a string, so they always either, the acceleration can't be measured as up or down, because if one of them goes up, the other one goes down. What's that tell you? Up and down aren't directions of acceleration here. Not for the system. The system is clockwise or counterclockwise, okay? Very important idea. Want to get it right now, okay? So the net force is the sum of all the forces, which equals F grav M1 minus F grav M2, right? Okay.
Why is there a minus?
Because one of them tends to accelerate in the negative direction of rotation, the other in the positive direction. They tend to accelerate the system in opposite directions. If it was plus, then having the same mass on both sides would tend to accelerate the system, right? If you got the same mass on both sides, nothing accelerates, okay? If you had a plus there, though, that would tell you that your net force is positive, and that would imply an acceleration because of what I'm about to say next, okay?
Are those just the magnitudes, so neither of them are negative?
There's no arrow over them, so they're the magnitudes. Yeah. And I don't put arrows over them from what I just said before. These things have directions in space, but this system is moving either counterclockwise or counterclockwise, right? There's no net movement in space because part of the system's moving up, part moving down. That just makes it impossible to describe the motion of the system in space. Now, actually, there is a way to describe it in space by the vector angular velocity, okay? We don't want to talk about that. I mean, you'll, of course, see that in multivariable calculus, those of you who are taking it, but otherwise don't worry about it. And don't worry about it right now, okay?